Hi everyone. So today's experiment is about centripetal force, and then you will be using the manual, and this time it was very hard to find a simulator that really pretty much exactly mimics what we have in the lab. So as a result of that, more or less today's experiment is going to be more of a data analysis. What's going to happen is I'm going to give you the data and you will read the theory. You will try to understand what is happening here, and I'll try to explain a little bit for you as well. And then you will go ahead and then follow the procedures. So for instance, what you will be expected to do is the very first part of the experiment. That means the manual centripetal force apparatus. So here's the experimental procedure. So at every step, the manual is going to tell you what data to pick up. Then what is going to happen is you will just literally get that data from me, or I'm going to show you where you are going to find it. So just to give you some highlight, so for instance, when you read the manual, it may ask you this is a manual kind of centripetal force apparatus. So when the manual says bob, right? So this is the bob. Okay, so I'm going to try to mark it for you so that every time when you read it, I don't want you to get confused. So this is what the bob is. Okay. All right. So it has its own mass. Then when the manual says what is the mass of the bob, then this is what we are representing, or this is what we are referring to. Okay. And then this is a mass that we will be using as a direct measurement. So direct measurement of centripetal force. Okay, so what it means is for instance, at this point, as you can see here, there's a bob, and then this is where the radius of the rotor. Okay, so every time when you see something radius, then you may say what is it, what is the length of that radius? So this is what the radius of the rotation is. Okay, so then the distance from here to here, okay, then that is what the radius of the rotation. Okay, then in practice, what we normally do is we are going to go ahead and then spin the rotary over here, right? So imagine for instance, as you can see here, the bob is no longer attached with the pulley. Okay, so in the previous diagram that you saw, when we are measuring the direct measurement, what happens is if the string isn't really holding the bob, what would have happened is because you have a spring, so you have this, and then the bob is literally hanging on some kind of a string. So and then there is a spring that is holding it, right? Then the bob is connected to a spring, right? So what will happen is the spring will pull it, right? And then probably the bob is somehow like this, see? Then that's why we need and then of course here at the bottom, and here you have the pointer, you see? So the bob is literally away from the pointer. because the spring is pulling it, because if the spring has like, some kind of spring force in it, then definitely it pulls it away from where it's standing. So but if we connect a pulley and then a mass like this, then that's when this happens, like the bob is going to be directly pulled right on top of the pointer. Okay, so then whatever mass that you put in here until the bob comes straight down the pointer. Okay, so this is the pointer. All right, let me write it here because we have space here, we don't have any space up there. I don't want to make the diagram just too busy. Okay, so this is what the pointer is like. When you read the manual, when you read the procedure, when it says like the pointer, then this is what we mean. Okay, so now what will happen is, like, if, as you can see here, then when you rotate the system the way you see it here, what will happen is, like, the spring will start to stretch. Okay, that happens because of centripetal force. So now the spring is stretched. That's not because the bob is attached to some kind of weight over the pulley, but it is because of the tendency of this guy, the bob, somehow is going to be stretched. If the spring wasn't there, what would happen to the bob would have been like, it would have gone like in a certain away from the whole system, right? But now the spring is pulling it and then it's keeping it. But the faster you rotate this thing, the more the bob will move away from the axis of rotation, from this axis, right? So it's going to go outward like this as you spin it. So, but at a certain level, at the right rotation, at the right spin speed, what's going to happen is, like, this pointer and the bob will align themselves, right? So during that period, what you are getting is, like, you found the right spin that gives you a centripetal force that literally forces the bob just to fly over the pointer. Okay, so based on that, like, you're going to do the experiment. Okay, so then here is the procedure. The procedure is going to tell you, like, what steps that you have to do. Start from the very first part, and you will only do like part A. We're not going to do part B, but part A has like 3 different tables. So that means this is the end of it. So as I said, not expected to do part B. Then you will be doing, and then of course there's an optional part at the end, step 8. You're not expected to do it. So I'm going to provide all the data, as I said, for the experiment, but you will be just filling out those information. Like for data table 1, this has to be filled out. Data table 2 has to be analyzed, and of course data table 3 will be analyzed. Data table 4 is for optional, then you're not expected to do anything over here. Okay, having said that, like, what is the theory behind? I mean, definitely if you go through the circular motion video or the lecture video, then you will see those things. But the other thing is, like, what is centripetal force? So and like, for instance, centripetal force. Okay, so as the name implies, centripetal means center seeking. Okay, so centripetal means center seeking. Okay, so for instance, like, for instance, I have my earphone in my hand with of course not the AirPod, but the regular earphone, like most of you may have it in your hand right now. So if you it has like the little earbud here, and then and of course the string is there, and then if you whirl this thing, if you whirl it, okay, if you whirl it around over your head, for instance, in a horizontal circle, what will happen is like this thing is going to whirl like this, okay, in a circular path, right? And then there is something that you will feel. You will feel a tension here. Okay, you will feel the string taut, right? So why do you feel that tension in the string? Why is that happening? There is a reason like that this thing is happening, because for several reasons. It's because of the centripetal force, okay? Because the centripetal force. Why? Because this little mass, or the airpod, is being constantly pulled towards the center. Why it has to be constantly pulled? Because, for instance, if all of a sudden by accident, or if, like one of your friends come in and like cut this string, what will happen is like this mass is going to fly off like this. Do you get it? Right? So it would move with a certain velocity, and then it's going to go in that direction. Of course, the speed of the ball, let's assume that, or the ball that is rotating around that circular path is constant. Okay. Now you can consider it like, let's say now the string. You can imagine like when the string goes here as well. All right. Again, like if your friend and then comes it and cuts it like that. In what direction? So let's assume that the rotation is in this direction, okay? So in this particular case, now again, V is going to be like this, okay? Right? So if you see here, you have a changing V. V is not V as a vector quantity. If you consider V as even though like this thing is moving at a speed of like 5 meters per second around that circular path, even though the magnitude is the same, the velocity is changing because of the change in direction, right? So since velocity is a change in direction, velocity is a vector quantity, then unless both the magnitude and direction are equal, you cannot claim that the two velocities are equal. So that means the velocity here and the velocity here are different, because the direction of this velocity is in this direction, and the velocity of this direction is in this direction. The two are not the same. So that means there is a change in velocity. And what we know, if there is a change in velocity, then there is acceleration, defined as the change in velocity per unit time as a vector quantity, right? So this change in velocity might happen because of the change in magnitude. If a car is traveling in a straight line with an initial velocity of 5 meters per second and with a final velocity of 10 meters per second within 1 second, then there is an acceleration there because of the change in velocity, the change in the magnitude of the velocity. So that means an object rotating in a circular path with a constant speed has an acceleration because that velocity of that mass is changing direction all the time. So, if you were looking for the proof and all that, you can look at the theory video. But just to come to the point, the magnitude of centripetal acceleration, as we say here, like this centripetal, this acceleration, this little mass attached here, when it's rotating around a circular path, it has an acceleration, and that acceleration is known as centripetal acceleration. If there is acceleration according to Newton's second law, we know that there is force, right? Because we know that according to Newton's second law, acceleration is directly proportional to force, but inversely proportional to mass. Okay, and it's an equal equation. So those are the two reasons that we have a centripetal force. One is like there is a tension that you feel, right? That's the centripetal force. So that means if there is an acceleration, there is a force. But the magnitude of the acceleration is the magnitude of the velocity squared divided by the radius of the path. So that means if the magnitude is 5 meters per second, then you have to square 5 meters per second, divide by that by the radius of the path. If there's centripetal acceleration, then there's centripetal force. Magnitude, that absolute value sign is just to represent magnitude. We know that mass times acceleration centripetal. Magnitude. So the result, your centripetal force is going to be mass magnitude squared divided by this. So you're going to use this formula to carry out the experiment. So the experiment has two parts. One is a direct measurement of the centripetal force. Okay. So there is Fc, and then you're measuring it directly. Okay. And there will be Fc, and then of course, you can call it measured or calculated. Okay. Then using this formula. Then you will find the percent difference between the two, as we always do. Okay. As we know, percent difference is like the difference between the direct measurement and then the calculated one divided by the average of the two. And don't forget the 100%. Okay. So this is how you are going to do it. So then you will be using just this simple formula to fill out pretty much most of the stuff in the table. So here is my data table for the first one. Now what you will do is like here you're going to fill out like, so let's assume that when you read the manual, it's going to ask you the following, like rotate or spin the rotary of the apparatus 25 times or 24 times, 10 times, it's up to you. But I already chose that number for you. So we spun that thing 24 times, and then it took for the BAP 22.5 seconds to complete those 24 revolutions. Okay. So in other words, like this is what you're going to fill out. Let me use a red color. So the time is seconds. That's what we used. Okay. And then the time per revolution. Here is one important thing. Why do we need the time per revolution? We need to know, to find the magnitude of the speed of rotation. What we need to find is like, what is the time taken by the bob to complete one full rotation. We don't need the 24. The 24 is important because, you know, to make sure that like there is no any kind of you know, error like by virtue of rotating that thing for a very short period of time. Like when you spin it for once, it's very difficult like just to track that time, rather, you know. So how do you find this is time per, so it's just, you can put it as second time is that one, then per revolution. Revolution means one full rotation, right? So how do you find this? This is just simple. It's just like 22.5 divided by 24. And then you put in the result in there. Okay? Of course, you will show your work by the side here, how you calculate it, but you can put in the work here. I mean the answer here. You do the same thing here. 22.5 divided by 4, 22.8 divided by 4. Okay. Then now already gave you like the mass of the bob. You use this value, and I already gave you the radius of the path. So therefore, what you need to find here is just to apply the formula. Centripetal force here is equivalent to mass times the speed at which the bob was rotating divided by the radius, right? This is given, right? What value is it? Here is the value, 0.454. So for the first table, to find FC, right? You know, the calculated one. We know that mv squared over r. Your mass is 0.454 kilogram. Keep everything in SI unit, then your answer is going to be in SI unit as well. So I'm going to use this, and then v squared, and then the radius, I already gave you the radius. The radius is this much, 0.215. 0.215. Then you may wonder, like, how am I going to find the magnitude of V? V is the speed at which the average speed of rotation of this guy, when the bob rotates like in a circular path, then, you know, how much time did it take to complete one full rotation? You already have that time. You already found that time. Where is it? Here is the time. It's 22.5 divided by 24. I mean, you can do the math, and you can come up with it. So now, if you know the time, but do you know the distance? Of course I know the distance traveled by this little mass. It's the circumference of the circle. So that means the circumference divided by how much time it needed. But how do you find circumference? From your algebra, you know how to find the circumference of a circle, 2 pi r divided by, 2 pi r. You already know the radius. You have 2 pi, and the radius is 0.215, and you already know the time, the time that I mentioned, for instance, 22.5 divided by 24. You need to substitute it. Okay. Remember, the parenthesis comes first. Do this first, and then from there you find the velocity, or I mean the magnitude of the velocity. Then you take that velocity, this velocity, and you put it in here. Of course, you need to square it, don't forget that. Then that will be your F calculated. That's it, as simple as that. Right? So therefore, you know, the average speed, yeah, here I'm going to the average speed. So for instance, let me get back to here. When you found the circumference and the time over here, maybe you will want to take the average time, okay? It's better to take the average time because you have 3 measurements so that like you can have an average speed, okay? So you may take the average of the 3. That means the average of the 3 means you can make a correction within here if you want to. We took 3 measurements, didn't they? So plus 22.5 divided by 24 plus 22.8 divided by 24. Those are the average times that you have to find the average speed. Okay, if you can find the individual speeds, but it's all the same because you're using the same radius. Okay, and of course, since the 3 measurements, remember you need to divide this by 3 because you are finding the average. Okay. So the calculations, putting the values in the calculator, those are mostly of like a task that you will need to do it. Okay. So you can put in the average speed and then the computed centripetal force goes here. Then you have the direct measurement. Then you compare those two by using the data difference, the percent difference. Okay. So you do the same thing for table number 2. Okay. There isn't much difference. The only difference here is like you will have to use a new mass, and then you will see how the mass is impacting your calculation and your percent difference, because you will still have like the same direct measurement, right? Even though you changed the mass of the bulb, you still got the same direct measurement, and then you will see like how this thing is like. As part of your conclusion and discussion, you will see and say something about it, like, you know, how changing the mass of the bulb impacted the whole calculation and the percent difference and so on and so forth. Okay. Likewise, data table 3, you're going to do pretty much the same exact thing. You will find the average speed, you'll find the computed centripetal force, and then you'll find the percent difference. What do you see? A different item here. You keep the bulb at the very original one, okay, without an additional slot mass. What has changed is the radius here. You change the radius. Now the radius is different from the above 2, as you can see here and here. Okay. So you carry out like that, and that's pretty much what you're expected to do for today's lab. It's more of like a data analysis because we couldn't do any of a simulation. We cannot find, I personally cannot find a proper simulation that will somehow align itself with what we have in the manual. Okay. Thank you for your time. Then, I'll see you next time.